The second type of intermolecular force is a dipole-dipole attraction. So that is when we have two polar molecules interacting with each other. So whenever you ask a question of is there a dipole-dipole attraction, you're just looking for two polar molecules. When you have two polar molecules, there's going to be a negative pole and a positive pole. So that negative pole of one polar molecule is going to be attracted to the positive pole of another polar molecule. We have HCl right here to the right-hand side of the screen. So hydrogen is going to be very positively charged and chlorine is very negatively charged. They even have accurate sizes on those atoms. So that negative chlorine is going to be attracted to a different molecule, HCl's positive hydrogen. So remember that opposites attract and then the same repulses. So that chlorine is not going to be attracted to the other chlorine. But if I have another atom of HCl, the chlorine is going to be attracted to the positive hydrogen of a different one, and then the hydrogen is going to be attracted to a different chlorine. Example 12.2 says predict whether any of the following compounds can form dipole-dipole attractions between their molecules. So we're looking for it being polar. So sometimes you can get asked, is there going to be a dipole-dipole attraction between these two different compounds? Or they might word it to where if I have one compound in itself, will there be dipole-dipole attractions? So let's draw these out because it's not so easy to tell if it is polar just by looking at it. So COH, and there's going to be the lone pair on the oxygen. So is this a polar compound? Yes. It is asymmetrical, and there's going to be a pull towards that negative oxygen. So this one is definitely polar, and it will make dipole attractions. Next, CCl4. So if I was to draw this, it would look something like this. And don't forget the lone pairs because that will definitely tell us polarity. So these chlorines are very electronegative because of all of the lone pairs, but it's very symmetrical. So each of those chlorines are pulling in one way, but they're getting pulled in the exact same direction all over. So this is very symmetrical. So technically this would not have dipole-dipole attractions between their molecules because of the symmetry. The third type of intermolecular forces is hydrogen bonds. This is a type of dipole-dipole attraction, but it is stronger than other dipole-dipole attractions because there is hydrogen bonding. So in order for there to be hydrogen bonding, a hydrogen bond donor molecule containing a partially positive H atom must be bonded onto a nitrogen, oxygen, and fluorine or fluoride. So a hydrogen bond acceptor molecule containing a partially negative nitrogen, oxygen, or fluoride with lone pair electrons needs to be connected to a hydrogen. So those are the two steps to have a hydrogen bond. Here's the reason why it has to be a nitrogen, oxygen, or a fluorine. Those three have the most electronegativity. Chlorine does not count because even though it has a higher electronegativity, it has a much larger atomic radius, and so it would not count for this type of hydrogen bond. So you need to have nitrogen, oxygen, or fluoride connected to a hydrogen for this to be hydrogen bonded. And it also has to be polar. So figure 12.4 shows hydrogen fluoride. The fluoride is a lot smaller than the chlorine and it is very electronegative. So that very electronegative fluorine atom is going to be attracted to the positive hydrogen atom. So that electronegative difference is going to be around 1.9. And so that it's still a dipole-dipole attraction, but since it's much stronger, that is why we kind of say it's hydrogen bonding. Figure 12.5 is just showing hydrogen bonding in water and ammonia. So both water and ammonia have hydrogen bonding. So if we look at the Lewis structure, with water, of course, that oxygen is much more electronegative, so it's going to be pulling towards those oxygens. And then also it's an oxygen connected to a hydrogen. So that positive hydrogen atom is going to be very attracted to the negative oxygen atom. And then if we look at ammonia, so ammonia has nitrogen connected to 3 hydrogens and that lone pair. So because of that lone pair, it's kind of taking up this massive orbital on top and pushing those hydrogens down. So that means that there is a very asymmetric pull of electronegativity towards that nitrogen. So that's why ammonia is having hydrogen bonding and not considered symmetrical. If there was a 4th hydrogen, however, if there was 4 hydrogens, then it would be symmetrical. And it would not be having hydrogen bonding or dipole-dipole attractions. But thanks to that lone pair, it does. Example 12.3 says, which of the following substances can form hydrogen bonds to other identical molecules? So that's similar to that last question where if we have a solution of itself, will it have hydrogen bonds with itself? So in any time you don't automatically know the answer, the best thing to do is draw out the Lewis structure. And we also have to remember that with hydrogen bonding, we need to have a nitrogen, oxygen, or a fluoride connected to a hydrogen. So A, we just saw. We know that it's a hydrogen bond because it's just a hydrogen connected to a fluoride. And then C2H4. Well, we know that that can't be a hydrogen bonding because it has hydrogen, but it doesn't have any nitrogen oxygens or fluorides. So B cannot be it. C, HBr, we have a hydrogen, but we don't have any fluorides, oxygens, or nitrogens. So it can't be C. D, NH4, that's a possibility because we have nitrogens and we have hydrogens. Sorry, nitrogen. So if I draw this out, it's a positive charge on that nitrogen. This is a symmetrical compound, so technically this would not have any hydrogen bonding because there is no pull towards that nitrogen. There's just equal pulls towards the hydrogens. So that's why this one cannot be considered having hydrogen bonding because of the symmetry. And then lastly, H2, there's no hydrogen connected to nitrogen, oxygen, or fluoride, so that can't be it. So the only one it can be it is A. The last of the 4 types of intermolecular forces is dispersion. So what this means is at any instant in time, a molecule or atom may have an asymmetric distribution of electrons, forming an instantaneous dipole. So if we have a molecule, this is just a generic molecule, at any point in time, there's going to be a distribution of charge, where we're going to have a positive, a partial positive, or a partial negative charge. So at any point in time, the partial positive is going to be attracted to a different partial negative. So that's what we mean by that. So an asymmetric charge distribution in one molecule can induce a similar charge asymmetry in an adjacent molecule, forming an induced dipole. So what we mean by that is, let's say one molecule all of a sudden has that partial positive or partial negative charge. Well, in doing so, it might induce the molecule next to it also to have that charge and force that attraction. So the resulting short-lived attractions between instantaneous dipoles and induced dipoles are called dispersion forces. And we also refer to these as London or London dispersion forces. So any of those three is same thing as dispersion. Here's just an example of dispersion. So we have a generic isolated atom. If I have multiple of them in the neighboring atoms, if one of them becomes partially charged on one side, it might induce a partial charge on the other one. So it's being distorted towards that negative charge, but that partial positive is being attracted to that partial negative right there. So whenever you're asked a question about dispersion forces, the first thing you are looking for is it non-polar? If it is non-polar, that is when we have to use dispersion forces, because technically we can use the other 3 intermolecular forces to describe any other type. And even though it is a loophole that everything has a dispersion force, we are looking for the force that is most prevalent. So we use dispersion forces for the non-polar molecules. So once again, dispersion forces is the instantaneous dipole-induced dipole attraction It may last for only an instant, making this type of intermolecular force far weaker than dipole-dipole attractions. And technically all atoms and molecules exhibit dispersion forces, but once again, we're only using it to describe nonpolar substances because any other type will have a more prevalent type of intermolecular force.